Hello, welcome. Thank you for joining us. My name is Chelsea Rogers, and I'm the Marketing Program Manager at Cognella Academic Publishing. We will be starting the presentation shortly. Now, to get things started, I'm pleased to introduce Dr. David Blockstein, Senior Scientist with the NCSE and Executive Secretary of the CEDD. He will be moderating today's presentation. Good afternoon, David.
Hi, this is David Blockstein, and I want to welcome you on behalf of the National Council for Science and the Environment. As probably most of you know, we are a non-governmental organization, and as it says on the screen, our mission is to improve the scientific basis for environmental decision-making. We do that by working on both the supply side and the demand side, and today we are especially working on the supply side in terms of helping to improve education about the environment, especially from an interdisciplinary approach. The activity today, the webinar, is sponsored by the Council of Environmental Deans and Directors, which we call CEDD. CEDD is an organization of environmental leaders that is facilitated by the National Council for Science and the Environment. And as you can see on the screen here, we do a number of things in terms of getting together in summer in various places around the country to talk about environmental education, leadership of environmental programs. We get together here in Washington, D.C. in the winter, and then in the spring when we talk with people from the federal government. Hopefully they won't be still furloughed in the spring, and also with Congress. And if they're still furloughed in the spring, we're not going to Congress at that point. We also provide a lot of research on interdisciplinary environmental education. Some of this comes through committees through the Council of Environmental Deans and Directors, and occasionally we do sponsor webinars, and such as this one. And so one thing that would be helpful for feedback is if you do have ideas for additional webinars, either things that you would like to hear about or things that you might want to present, please do get in contact with us at the Council of Environmental Deans and Directors. I also want to take this opportunity to invite you to join us in Washington at the end of January for our 14th National Conference. The theme is Building Climate Solutions. As you can see here, we have some leading scientists and decision makers. The conference is an opportunity to exchange between science and decision makers and to advance solutions to the huge challenge that we have with respect to global climate change. And take a look at the website at buildingclimatesolutions.org, and you can find more about it. So turning to today, we are extremely fortunate to have Professor Dork Zahagian from Lehigh University, who is going to be discussing with us a new approach to teaching about environmental science. And this is an approach that he has pioneered with his students at Lehigh, and more recently has published a book, The User's Guide to Planet Earth, and that will provide background and information for those of you who are teaching and are looking for improving your teaching methods. So let me tell you a little bit about Dork, and then I'm going to turn it over to him for the actual presentation. So as I mentioned, Dork is a professor of Earth and Environmental Sciences at Lehigh University in Pennsylvania. He's been at Lehigh since 2004, where he came to direct their environmental initiative. He is a rather diverse academic career, beginning with a bachelor's in physics from RPI, and then he discovered that the environmental sciences were harder and more interesting than physics, and so he went to Rutgers for a master's in geosciences, and then earned his doctorate in geophysics, bringing the two together, from the University of Chicago. He has been at Dartmouth College, where he worked actually for the Navy as an oceanographer, at Lamont Doherty, at Columbia University, and at the Byrd Polar Research Center, which is at Ohio State University. He has also then went back to New Hampshire, at that time to the University of New Hampshire, where he led a couple of programs in the International Geosphere-Biosphere program, and also he's worked with the IPCC as an author and a reviewer, United Nations Environment Program as a reviewer, and he's taught a whole range of courses in environmental science, physics, astronomy, volcanology, structural geology, sedimentary environments, human-climate interactions, and other topics. So because of the kind of diverse teaching that Dork has done, he has been really thinking about what are the most effective approaches to be teaching about this interdisciplinary topic of environment. He has pioneered some of these techniques through an advanced course entitled Scientific Foundations for Environmental Policy Design, and more recently in an undergraduate introductory course in environmental science. And the User's Guide for Planet Earth and the approaches that he's going to talk about today are approaches that he has used for this introductory course. There's a lot more that I could say about Dork, but I'll turn it over to him to provide some personal information, not too personal, but a little bit of background about yourself as a human being.
Well, all right. Thank you, David. A little bit about myself. Well, I've been interested, as David said, in a number of different things. People ask me about the environment and about global change, and I can't put it better than Bloomberg did. It's global warming, stupid. And this was developed, I've been worried about this in all my years with IGBP and the Global Analysis, Integration, and Modeling Task Force, during which time I also got out into the field. I love field work where you can actually get your hands dirty, but you might not want to try this one at home. This is me on an extension ladder on a cliff that is holding the equivalent of a chainsaw, but it has a rock drill bit in it to drill holes out of that basaltic lava flow. But I did not fall. It's okay. Down below, I discovered when I was in Tibet doing that sort of thing that the monks actually do go to pubs and sidewalk cafes and talk on cell phones. So it is a modern society. Who knew? And this funny-looking thing is actually a volcanic ash particle that I've been studying for some time for my interest in volcanology, and it turns out that ash particles do funny things because they're so small and oddly shaped when they go in the wind, and I've been exploring that in a wind tunnel, which is kind of fun. Now, what is this? This looks like the cover of the previous IPCC report. The brand new report is just out last week. I discovered in Mongolia the best way to get around in the field. This is the way to go. Why ride a horse when you got a camel?
And from the NCSC and CEDD perspective, we of course like camel because our climate change education project is the CAMEL project, Climate Adaptation and Mitigation E-Learning. So we're going to have to put this picture up on our camelclimatechange.org website.
All right, now you have a mascot. Good to know. When I'm not doing any of that, if it snows, you'll find me outside in the North Country, and that's nice. Or when the wind blows and the water is unfrozen, you'll find me outside as well, taking advantage of some wind energy, one of my pastimes. I discovered early on that every kid needs scouting for something. It may be for skills, it may be for confidence, it may be for socialization, maybe just for fun. And maybe all that time as a boy myself outside got me interested in environmental issues. So we live in a natural environment, indeed. How about teaching it? Well, I got a little bit worried about how things were being taught in the books we were using. It just wasn't working. There had to be a better way. So I went and took the bull by the horns and wrote a whole book the way I thought it should be. It's kind of a new kind of textbook that built on what I had been working on and developing in my classes. And so I figured, well, why not make a proper textbook that anybody can use?
But, I mean, Dork, we do have a lot of environmental science textbooks. What did you think, or what do you think is lacking, and what's the need for something that is a different approach, as you're describing here?
Well, I thought we needed something a little bit different than what we had. And what kind of motivated me to do all this is that I kind of noticed that a lot of the students I was encountering were losing the ability over the years to think for themselves. They've just been regurgitating what you feed them. Now, of course, every student's got the internet right there in their pocket, and a cell phone, a tablet, what have you. And it became clear as years have gone by that everybody needs to understand the workings of the environment and basic environmental science so that they can assess what's going on in the world around us. Not just the majors, environmental science majors, but everyone. And that's mostly who I get in my introductory classes. It's not just environmental science or earth science majors. It's business students, it's some engineers, it's arts and sciences students, all kinds of students that I'm getting in the classes. And everyone needs to know. The problem was that the textbooks that I'd been using and that seem to be available all over the place are so thick and full of stories that they kind of dilute the science with all the storytelling and case studies and that sort of thing. And what seemed to be even worse is that all the data and all the figures and the charts and the graphs are pretty much out of date by the middle of the semester. So you have this great, big, huge textbook that is not really useful later, on top of which, and perhaps this is the worst of all that put me over the edge, the textbooks have reached astronomical prices. They just got so expensive that when kids have to spend more than $100, $150, sometimes $200 for a textbook, it gets a bit onerous. So I thought that was pretty bad. So we have kind of a situation that I was dealing with. Right? This is basically what I just explained. Now you have it. You can see it. So this was very frustrating to me. I was trying to get students to think. It was difficult. Frustration was in getting the students to think instead of memorize and regurgitate. So I felt a little bit like Sisyphus, and it may appear that I'm stronger than I look. Right? I won't reveal the magic here.
Photoshop.
No, it was really on a slope. It was a slope in California. So it brought me to to articulate the philosophy that I had kind of been developing about teaching in the 21st century, where I realized there's no real sense in trying to cram lots of facts and figures down the students' throats when they can look these things right up on the internet at any time, right in their pockets. Really, we need to focus on the key concepts, to stress the processes and the fundamental scientific analysis involved in environmental science. They can look at the details anytime. In a lot of the books, you read all the horror stories of the poor people and the environmental issues and the problems and the catastrophes and all these stories that seem to dilute and maybe even obscure the science itself. So the students come out of class at the end of the semester thinking that environmental science is all about stories. It's almost like a history lesson. That's not what I'm trying to get across to students, and I don't think that's what they need, especially in the 21st century when they can look these things up anytime, inside or outside of a book. What I think these textbooks need to be now is, first of all, cheap enough for them to actually buy, short enough for them to actually read the whole chapters of each section that we're doing, and should be written clearly enough that they can understand the concepts. what I'm trying to get to is teaching them to think for themselves instead of regurgitating just the facts and figures information that we just told them.
Okay, so this all makes sense probably to everybody who's listening on the call. So then the question is, how do you translate this understanding and approach to actually teaching about environmental science?
Well, what I've been doing is developing a number of strategies that prevent students from doing exactly this. I try not to make them copy down lots of notes, scribbling what they're seeing on the board or scribbling so fast of what I'm saying that they can't pay attention to what's going on and they can't follow the logic and the science. I want them to be able to focus on what I'm saying in class rather than scribbling a lot of stuff. So what I've been doing is I provide the charts, the graphs, the numbers, all the information, the content that they need with the lecture notes. We have PowerPoint. We just put it right on whatever it's going to be, a Blackboard, course site, what have you, and I give it to them. They can have the whole thing. So they start with that. Then on top of that, they can scribble down whatever they want. They can put circles and arrows and underline and stress whatever they like on that, either on paper or on their laptops. The hope there is that this can develop their reasoning skills to follow the science rather than just trying to scribble all the content. Also, I've been trying to encourage student engagement in the classroom. Sometimes I have very big classes. Some have been as small as 8 students. Some of my intro classes have been as large as 270. At the moment, I have one that's 185 or so. Still, it's not impossible to engage the class in real time. And so I ask questions of the class that I didn't just answer. It's easy to just say something and ask them what you just said. That's regurgitation. You got to ask them what you didn't answer to make them think. For example, you're discussing Milankovitch cycles and climate and orbits in the sun, earth, moon positions. So ask them, okay, what time of day does the full moon rise? They should be able to answer that from that. Nobody can ever answer that. You might think about this. You've seen a number of full moons rise. What time of day does a full moon rise? Well, think about it. Well, it doesn't depend on much. It depends on the season, maybe, right? Full moon rises at sunset. It's almost like asking what color is George Washington's white horse, right? If you think about it, the sun's got to be on one side, the moon's got to be on the other side for it to be a full moon. So this is what the kind of thinking I'm trying to engage my students in. On homeworks and exams, I pose questions very often that don't have a right answer. Because it has a right answer, and some do. I mean, you have to ask questions that are maybe a calculation, something numerical, something factual, fine. But that's not the ones that make them have to think for themselves. Examples of questions that don't have a right answer. Talk about energy and alternative energy sources. Ask them, what is the most appropriate mix of alternative energy sources in the portfolio for the local area where they live? Right? There's no particular right answer for that. The whole point is you've got to ask them why they think this is an appropriate mix, given the resources, the environment, and the resources in the area. Or what's the optimal configuration of developed and natural or pristine environments of a new land surface, right? There's 2 extremes. You could make a checkerboard pattern between paved and developed and national parks at the a checkerboard of acre size squares, or you could say leave North America, Africa, and Australia alone and develop the rest, right? These 2 extremes. Well, you got to justify where in between those would be useful based on what you know about the environment. These are things that make them think, but it has no correct answer. How about the trade-off between population and per capita consumption? Right? There's a certain amount of resources, a certain rate of provision of environmental goods and services. That's a total amount. How should that be distributed? Well, it has no right answer. Depends how people want to live. So these are the kinds of things that you want them to think about. It's not just regurgitation. I tell them the first day of class, don't believe anything you read. Don't believe anything you watch on TV or hear on the radio. Don't believe anything anyone tells you. Don't believe anything I tell you. Figure it out for yourself. That's what science is about. And right off the bat, I want to question their assumptions. They should really examine what they're assuming, because science is based on a number of assumptions that are not usually stated. For example, solve this very difficult mathematical equation. Well, some of them look kind of funny at me when I show them this. Okay, eventually sheepishly they say, well, it's 4. Great, lovely, we solved it. Now, what are we assuming when we say that? And they come up with various things. They don't come up with the obvious thing, which is that they're assuming that we're in base 10, or anything over base 4. Right? In base 3, 2 plus 2 would be 11, for example. Right? They just assume it. So they got to examine the assumptions, and that is the way to begin thinking scientifically. So I give them a homework assignment. So let them look at anything. It doesn't matter what kind of article in the paper or online or whatever. It doesn't have to be a scientific article. But what don't they tell you that maybe will be useful to know? What assumptions do they make? What would they have you believe without providing any evidence or information? And are there discrete conclusions drawn, or are you left to infer some result, all right, and conclude something for yourself that may or may not be correct? And so I encourage them, of course, they should be doing this every time they read anything.
So what have you learned then from using this approach that you want to share today to help your colleagues here to become better educators?
Well, there's a number of tactics you can use. I call them tactics, but it's it's basically what you do in the class. For one, of course, de-emphasize memorization, focus on conceptual understanding, of course, and no doubt a lot of people listening have already started doing that and tried to do that. But more specifically, the class lecture notes, the things that you show the class, this can include electronic material, PowerPoints, with up-to-date figures, graphs, charts, whatever information you want, and give it to them. Give it to them right up front so that they have that. That's the starting point. Then when they come to class, they already have that, and they can listen to what you have to say. Now, this is the place for pretty pictures. What you're showing in class, the latest photos from some environmental disaster, right? I mean, here's a nice environmental disaster for you. All the things that you want to show that may be right up to date. You can update these things the night before the lecture, of course. The factual content that you show places the environmental concepts that you're trying to explain into context. The content, as far as I'm concerned, is just a means to the end. The end that you're trying to achieve, or that I'm trying to achieve anyway, is scientific understanding and critical thinking about the environment, not just memorization of a bunch of facts and figures. And this is why when I wrote this textbook, I didn't fill it up with tons of facts and figures. Right? We do that in the class periods, plus that gets out of date very quickly, and they can look that up on the internet pretty much any time. So, in my view, a book should focus on explanations of how things work, how the functions are in ecosystems, how the greenhouse effects work, how all of the environmental parameters that drive the functioning of the Earth system operate, undiluted by all the stories in which they lose the concentration on the scientific function.
So you've written this textbook, you're pioneering an approach with your own students, and I know some others have already adopted this. Are there other resources that you and your publisher provide that could help people to teach not just with your textbook but with this new approach?
Well, sure. There's more pragmatic help available in the classrooms. I mean, I find that faculty find the charts, imagery, ideas for things to display and show as supporting material in the classroom very useful. So I've gone ahead and compiled a number of sort of PowerPoint presentations, as you will, full of slides that are focused on each of the concepts that we're trying to explain. And this is, it goes chapter by chapter, topic by topic, available to anybody who wants to sort of adopt this philosophy. It takes a little bit different imagery that you're going to show the students, because you want to focus on the scientific comprehension of the concepts, and then with each of those show an example that it's up to date to put it into context. So it's a little bit different from the information regurgitation approach that we've seen so much. So we focus on the concept. Now there's some things that we can look at. For example, feedback's a very fundamental concept. Now we want to relate that to something that students can relate to. So, well, up in the North Country where we are, it snows up here. The kids ski. So, all right. So here's some skiers. Now this negative feedback guy, by the way, these are all my son, is skiing on a powder day. Not much powder, the lower one's much deeper and nicer. When powder hounds don't like each other, right? Once one goes down a slope, it's ruined. They've spoiled the virgin powder. Nobody else wants to go down that way because they don't want to cross the tracks. It has ruined that nice soft feel of the powder, right? That's a negative feedback. Once one goes down, the others shy away. As opposed to the bump skiers here, well, once enough people go down, they make tracks, they make little bumps of snow. Their bumps are made, the moguls are made by skiers. Then the more that go down, the better they get. The better the tracks get, the more they go, the more they go. It's a positive feedback. And if you want to get into the particle physics, the negative feedbacks are like the fermions, where once an energy level is occupied, no more can fit. Or the positive feedback is like the bosons, where it's the more the merrier. So feedback concepts are fundamental in environmental science. You can figure out the doubling time of exponential growth. Now here's where you have to deal with math. The students have to confront math, and a lot of my environmental science students are a little math shocked or math weary, math averse.
Intimidated.
And so we show them it's not that hard. It's trivial, in fact. So when you come down to the rule of 70, right, which everybody's supposed to know, the rule of 70, you should know, where does it come from? It's not that hard to derive this stuff. So that's how you figure out the doubling time of all sorts of things. How about Heisenberg uncertainty? Now here's a concept that comes from physics. Now we're not going to get into the quantum physics of this, but basically the act of observing something alters what's being observed. And I tell them, what if you a mom is going to go look at their kindergartner in the kindergarten classroom, sit right next to them in the classroom, see if the behavior is going to be the same as it would be if they weren't there? Of course not, right? And this relates to all kinds of human perturbations, land use behavior, because when we build prognostic models and we tell the population about it, they may not like the result of that, and since the result of that is the result of their actions, they may change their actions. So that's Heisenberg uncertainty. And finally, I say, well, okay, now imagine your grandmother. Your grandmother comes with you to a fraternity party. Would you behave any differently? Maybe so, right? Now, you cannot plan your path through this crowded shopping mall. And all my students have been to a crowded shopping mall at one time or another. You cannot walk across this mall with your eyes closed because you cannot plan your path in advance. People are moving in front of you, they're changing their course. You have to play it by ear a little bit. You have to adjust as you go, and then, of course, the basis of fuzzy logic, which we need to apply to much of environmental science, especially when it relates to global change. Now, a lot of students don't know anything about hydrology, where the water comes from, where it goes to, and they need to know some basics. They don't realize that surface water, when they see it on a lake or river, is just a surface expression of the water table, the groundwater, where the topography dips down below the water table. And if you build a dam to make a lake, you've actually got to impound more water in the groundwater surrounding it than in the lake itself. Right? They also don't realize that spring water isn't any better than groundwater from a well. In fact, spring water is just groundwater that comes up to the surface and has the opportunity to be contaminated at the surface. So they should think about what they're getting in their bottles. Agriculture has a number of impacts on the environment, maybe the biggest impact so far as land use is concerned, the other one being emissions, of course. So on land, we are farmers. We've learned to grow food. Lovely. In the oceans, though, we're still hunters and gatherers. Until recently, we've begun aquaculture. Lovely. Great. But we have to feed our farmed fish something, right, to let them grow and eat. Well, what do we feed them? We go out and catch other fish, and we feed them that. We catch them fish just from regular hunting and gathering. Now, we recall that from trophic levels, every trophic level you go, you lose 90%. You lose 90% of the energy, and therefore, we'd be way better off eating the 100% of the fish that we're feeding the farmed fish than we would be if we feed the farmed fish and eat the salmon instead of the herring or mackerel. The community effect is fundamental to ecology, as I'm sure many of you know, and we have to explain about how this works. And of course, one obvious example is the fisherman catching the sea otters in the act of eating of fish. Fisherman's out there and say, hey, he's eating my fish. He wants to catch them and sell them in the market. So he shoots the sea otters. Didn't know, though, that the sea otters also eat the sea urchins at the bottom, and the sea urchins gnaw on the bases of the kelp and thereby kill the kelp. And the kelp forest provides the nursery and the food for breeding and growth and protection and habitat for the fish. So without the kelp, there's no fish. Without the sea otters, there's no kelp. So the kelp are basically making, the sea otters are basically making fish. They kill the sea otters, they kill the fish. And so that's the community effect. And this is a fundamental concept in any functional system, especially in the environment. Well, of course, everybody knows about El Nino, but they need to know how it works. You know, what drives it, how it works into atmospheric and ocean circulation. So that's key. And, of course, a lot of talk now about sea level rising. Why? Glaciers are melting, oceans warming, we're dumping water into the ocean, but we don't know how much water we're dumping in the ocean or holding back by building dams. A big question, but it's something the students need to confront, especially we're near the East Coast where a hurricane hit last year, and that was a big problem. Hurricane Sandy, compounded by sea level, becomes relevant. Speaking of the sea, many of the students have never even heard of the issue of ocean acidification. So we talk about climate change. Okay, how do you remediate climate change, right? There's mitigation adaptation measures you can take, but if you can put orbiting mirrors or sulfate aerosols, that's not going to help ocean acidification, which is from the CO2 being absorbed into the ocean by the solubility pump, brought down by the biological pump, and if the biological pump shuts down, then we're having big problems, not to mention the marine ecosystem. So, so we have a situation, and there's, here's my sort of proposed solution in a nutshell, right? Focusing on fundamental scientific concepts, reasoning skills. Don't take up their time in the classroom scribbling and scribbling. Let them listen to what we're saying in the classroom so they can understand it themselves. We can give all that information to them. We have electronic methods now. And so far as books are concerned, they really need to be cheap enough to buy, short enough to read, and clear enough to understand. Now, it may be that we can change the way all students think about the environment by this different approach. Maybe it's just a small step in what I'm hoping is the right direction. Hopefully it will help. This is our home. It's kind of the only one we got, according to a famous wombat. So we better know how it works. The more of us there are, the smaller it gets. The more we rely on a heavily stressed environment that is supposed to provide goods and services for all of us. Our students had better understand how it works. Let me end there and open up for questions from everyone, if we can arrange that.
It's great, Dork. Well, thank you very much. While people are queuing up for questions, either by typing them in the text box or by raising your hand so that Chelsea can call on you. Let me just ask, so how is, this all sounds great, but let's talk about operationally. What's been the reaction of your students? What have been the things that have gone well? What are the things that haven't gone quite so well?
Well, the first thing they reacted to was the price, not having read it at all yet, right? Without opening the book, they looked at it and said, "Oh, you mean it's not $150, it's $55? You know, great." So they were smiling from the get-go, but it was like, okay, now how about reading it? Well, it turns out they're actually able to read the whole chapters. I mean, they're pretty short. They're to the point. They're focusing on the concepts, and they seem to like that a lot. I've gotten a lot of good feedback, and when I tell them, because I said, hey, you're my students, I wrote the book, other people are going to use it, you guys are the guinea pig, tell me what should be improved, what should be fixed. Well, they found a couple of typos, but by and large, they really like it.
Okay, so here's a question that somebody typed in. Your focus here is on the science, but we know that science doesn't occur in a vacuum, especially environmental science, and certainly with climate change, there are a lot of politics around there. So how do you deal with the students who are coming at you with focus on the politics of climate change, more so than the science, perhaps?
Yes, well, that's actually a good question, and that's one that we have to address big time. In fact, that's some of the National Council of Science and the Environment is also helping to address at the larger scale, and the students need to understand how science operates independent of politics. Politics must never drive science, only societal need could drive science, but science can and should be used to inform the policy process, which of course now I have a whole other graduate class in Scientific Foundations for Environmental Policy Design, different story, but at the introductory level, I do spend some time at the end, which is relating what they've been learning to how policy may be developed, and I can show examples of where things have gone awry, say with the Kyoto Protocol. Here's an international protocol that should work. Work to do what? Well, here's one of these misnomers that some of the students, most of the students perhaps don't understand. Even if we had signed and ratified the Kyoto Protocol as a nation, that would not stabilize climate, it would not stabilize atmospheric CO2, right? It would just stabilize at 1990 levels, the rate at which we add CO2 to the atmosphere, right? So it's a stocks versus a flux concept, another big concept that I didn't discuss just now, but one that has to be discussed. So these are the kinds of examples one can show for those interested in science. In politics, I have not encountered any students, I'm happy to say, who claim that they don't believe in global change. And my response to them would be, if I did, that I don't believe in it either. It is not something amenable or subject to belief. This is science, not belief.
Or as Richard Alley says, well, I believe in the laws of physics, so maybe that's a belief.
Yes.
So with this book, you've added enhancements in terms of the PowerPoints and other resources, but why have a paper book at this point in the 21st century? Why not just do the whole thing online?
Well, that's a good question. In fact, all the long, big, verbose, coffee table volume, I call them, books, have electronic versions you can get now. So, you know, how is this any different? Well, I've looked at these electronic versions of the textbooks, and they're just an electronic version of the same thing. It's not. There's no difference in philosophy. No updating for 21st century where students have facts and figures in their pockets, literally. It's just electronic. So the reason to have a paper, of course, it's paperback, and of course it comes electronic version, is because it's shorter, it's to the point, and it's cheap. So basically, it's very different whether it's paper or electronic than the other ones that I've had to use over the years and have been frustrated with.
Okay, so take take us into your classroom now. So you have a different approach that you're trying to use. You have a different textbook. So you know, pick a lesson, whatever. Can you describe sort of when the students come into your classroom, and maybe also just a context just about how many students you've been teaching, and then kind of walk us through a class period in terms of what's actually happening and how you're providing that interactive environment.
Sure. Okay. Well, I mean, they come in. I start talking to them as they file in a little bit, just to try and keep it light. There's at the moment I have about 185 students. It's a big lecture hall, so the challenge is to engage the interaction rather than just be at a movie theater, right? So I try to speak to them, even the ones, especially the ones up in the top row, farthest away. Each class period, I try to keep it a specific, coherent title from start to finish, rather than get up to where I get, and then the next class they do something else and start a new topic in the middle. I try to make them coherent classes. So it's like, today we're going to talk about soils, or today we're going to talk about the ocean, or whatever. So we go through that, and I present various facts and figures. I present pretty pictures after the concepts that I show them right up front.
Excuse me a second, George. So now, will they have read the chapter on soils beforehand?
They better.
Okay.
They will not only have read the chapter on soils, which is short and readable, but they will have studied, if they do what I tell them, the PowerPoints that I'm going to show them.
Okay.
So they will already have in front of them, having seen, and I try to get the PowerPoints up at least a day before, because they're up to date, but sometimes it's been sort of 2 in the morning by the time I've gotten them up there. And so that they have them before class so they can see it and see where we're going. Then they can focus on the explanations that I'm providing them and listen instead of scribble. And I think that's a key point. So I get through the class, and partway in, either I tell them some little story or joke, or I ask a question. Maybe it has no answer. I kind of make them think. Or I draw out some examples. Okay, have you experienced a flood or a storm, or ever seen fall leaf colors, or seen robins coming back in the spring, whatever it is, and they give get examples from their own experience, and move on with the rest just to keep them engaged. At the end, sometimes I ask another couple of questions before the end of the class period, and of course every week there's homework that they're doing, and sometimes they have questions about that, and that's fine. So I try to keep them engaged throughout the course of the class period. My class periods are 75 minutes twice a week. Some people do 50 minutes 3 times a week. Same difference.
Okay. And so with this interactive approach, then how does that then be carried out in the out of class? I mean, the reading, but what kind of homework and what kind of assessment approaches do you use?
I have, basically it's exams and homework. With a class of 185, we don't try to take a field trip. Sorry. This is not a laboratory class. There are some versions that are laboratory classes, but at Lehigh we have a separate laboratory that sort of covers a number of different environmental classes that are not this general environmental science class. But with 3-hour exams and a final exam, and in fact I drop the lowest of the hour exams. With very large classes, it's hard to do makeup, so I say, hey, you get sick, just drop it. And the homeworks. So I count 100 points per hour exam, 150 points for the homeworks over the course, 10 homeworks of 15 apiece, and a final exam of 150 points, making a total of 500. Point is a point, and they can rack them up. And that's the grades. And some of these students come into the class more concerned about the grade they're going to get than about learning environmental science. And I work as hard as I can throughout the course to alter their perspective on that.
Right. And so what are you learning in terms of the student outcomes, and what like compared to when you were teaching this class 5 years ago and doing it in a much more traditional way, what kind of outcomes are different in terms of student learning?
Well, for one, I'm finding it a little bit easier to engage the students. This year, now that I'm using this new book and approach, I mean, the approach I've been doing, but it's been kind of using this approach with the old textbooks was kind of trying to put a round peg in a square hole a little bit. Mm-hmm. That was a problem. Now that I get to use my new book, the students seem to be more engaged in the classroom. But interestingly, I just gave my first hour exam. And I thought I made it pretty tough, maybe tougher than previous years, and the students actually did better. I have no explanation for it. It may be just a smart class, but they actually seem to be doing better. Hopefully, it's because they're understanding the concepts and the information and not just trying to memorize and regurgitate. The acid test will come at the final exam where it's too much to try to memorize. There's so much material in a class like this. The content is huge. But if they can learn the concepts, they can figure out the rest themselves. So if they've really done it well, they'll do well on the final.
Okay. So it doesn't look like we're getting any more questions from the people who are logged in here. So let me just, I guess, ask just talk about one other thing that we talked about a little bit here, which is I know that there are several faculty members who, even though the book just came out over the summer, are already teaching with it. For those who are interested in, obviously if you want to explore the book, you can get an examination copy from the publisher, but in terms of yourself, what kind of interaction are you willing or interested to have with people who want to learn more about this approach, or be providing some feedback to you in terms of their teaching, things like that? How, are you just sort of dropping this approach and doing the webinar, or are there some opportunities for interaction?
I'm hoping this is just the beginning. Any feedback from anybody would be greatly appreciated. I'd like to know how it's working out for anybody that uses the book, that even takes this approach, and any modifications that they suggest, either to the book, to all these sort of PowerPoint things, chapter by chapter for in-class presentation. Any updates of those or suggestions, I'm all ears, and I'd very much appreciate, in fact, any input. So this can be, it's not so much a community, project, as much as any feedback I can get can only serve to improve the textbook, the resources that go with it, and hopefully all of our classes.
Okay, that's great. And one other thing we might want to think about is that if you're not in Mongolia or other place this June, not only will we have our Council of Environmental Deans and Directors, which is a group that is by membership, but also the Association of Environmental Studies and Sciences, AESS, which is it's also a membership organization, but it's by individuals and is a little more focused on the actual pedagogy and teaching approaches. And so maybe we could think about having a workshop or some sort of an interactive session at that meeting, which is going to take place June 11th through 14th at Pace University in New York City.
That would be great. In fact, by then we'll know a lot more about feedback from the various people that have been using the book and using the approach, and hopefully make this better and better as time goes on. Sort of a living document.
Let's turn it back to Chelsea Rogers from the Cognella Academic Publishing, and just for some final context and information for the participants in this webinar.
Great. Thank you, Dork and David. That was very insightful and interesting. We'd like to thank everyone for attending. As a reminder, this webinar was recorded, and we will be sending you a link. Thank you very much, and have a nice day.